And the first time that I started learning about research was really in year 7 in medical school. And just like many of my classmates and friends, I was rushing over the concepts so that at the end of the day, I could have a defense. And I was so interested in research that I started reading on my own, trying to understand what all these statistics in research is all about. And I went to do a master's in epidemiology at the University of Bristol in the UK. And I realized that it looks like I learned research the wrong way. Hello, can you hear me?
Yes, we are getting you very well.
Thank you very much. So it looks like I felt when I was in the UK that at some point I was learning it the wrong way. And I actually understood that the sole purpose of research is to provide an answer that is precise enough and unbiased enough to be applicable in real life. And this kind of changed the whole way, my whole way of appreciating research. So when I came back, I said, okay, let me try to produce a program that is going to make people talk about the basics so that we can do like less research, but research of good quality. With my little experience with students in medicine, because I have coached over 200 of them since 2018 that I finished medical school at the Faculty of Medicine and Biomedical Sciences, I realized that lots of research that's done at the thesis level can't be used to do anything. The first reason is because the data is not reliable. Students don't have funds. They just try their best to go around, collect data, and then come back. And then their supervisors have a lot of students to supervise. There are many things that make that. At the end of the day, if you really want to check whether the data is accurate enough, whether the research was conducted in the way that was described, if you check, you realize that most of the products of research activities around are things we can't use to do anything. And if you use it to do things, a lot of people will die because public health is more decisive, more the impact of errors in public health is larger than impact in clinical research. Because it's true, if you make a mistake in a hospital, like Prof. Ngufak likes to say, the family is going to have issues, like the family is going to be sad. But that's kind of limited to the person that you were treating and the family of that person. But if you make mistakes in public health, and then people collect data that's not reliable, and then they make conclusions that are not valid, and then the authorities apply these conclusions, the number of people that are going to die is catastrophic. So those are the motivations of this basic health research series. I'm not saying that I know it all. I just want to kind of ask people to, hey, can we think about the basics? Can we stop a little bit and try to reorganize? Okay, thank you. So that was my introduction. We're going to go straight out into the core. The reason why we are here is random error. If you have any questions, please just feel free. Just switch on your mic and speak into it. I'll be really happy to answer any questions. So these are my main references. So we have Medical Statistics by Jonathan Stern. So the book on the left, Jonathan Stern was my biostatistics and epidemiology teacher, like advanced epidemiology teacher at the University of Bristol. He is just amazing. I would have loved to invite him sometimes, but I mean, he's so busy and I don't know whether he'll have time to talk because he's so inspiring and he really knows how to make you dream about research when he tells you about a principle. Okay, the person on the right, I don't know him, but it's someone who is very cited in terms of causality, in terms of causal inference, how to avoid bias. I think this is one of the heaviest book out there talking about the up-to-date methods to avoid bias and to treat bias. in observational studies and experimental studies. Now, if you are not versed with certain terms I'm using, feel free to interrupt me. And this presentation was kind of reviewed in an informal way by Dr. Caitlin Wade, who is one of the program directors of the Masters in Epidemiology at the University of Bristol. She made some suggestions and corrections, which I took into consideration. So thanks to her. Okay. So I'm talking about medical research, but really I'm going to be talking mostly about epidemiology, which is the study of diseases and just any health related issues in a specified population. So in epidemiology, we are usually interested in various kinds of parameters, such as the proportion of people suffering from a certain disease, also called the prevalence of that disease, or the strength of the association between an exposure and an outcome, which could be measured using various estimators, like the risk ratio, the odds ratio, the risk difference, relative risk, difference in means, etc. So generally we want to quantify the amount of disease in the population, and we want to know what are the things related to this disease in that population. And we try to measure all of those things because epidemiology is mostly a quantitative science, a quantitative research subject. So the point I'm trying to make here is that the result of a study is usually a number that gives us the amount of something, amount of disease, amount of the strength of the association. So it's an intensity, it's an amount. And that amount should reflect the truth. That amount that we are obtaining at the end of a research process should reflect the truth and should be precise. Those are the two big things that determine whether research was of good quality. So basically what we generally do is that we have a question, we have objectives, we put up a method, we elaborate a method to collect data to answer the question and to attain the objectives. And then we do some analysis with the data collected. So all this process, in the course of all this process, there are two things that will happen. They always happen. We lose precision and we lose accuracy. Precision and accuracy are being lost during a research process. Now, the question is that how can we have zero loss? It's not possible. The question is, how can we lose just little and have at the end of the day, the amount of error that we could manage? So the next slide is going to talk about error. So error is the difference between the result obtained by a study and the truth. So the truth, we don't know. We never know the truth. We only have certain indicators of what we think could be the truth. And since we don't have the truth, whatever thing we say at the end of a research endeavor is an approximation of the truth. So the game here is that we believe that if we conduct a study with enough caution, our answer will not be the truth, but it would be a helpful reflection of the truth, a helpful approximation of the truth. So that's it. So we have two types of error. We have systematic error, we have random error. So in each result of studies, if you take any paper and you read, critical appraisal of a paper is the assessment of the precision of whatever estimates that you have and the assessment of the amount of bias of systematic error. We're going to look at systematic error next Saturday. This Saturday, we'll focus on random error. And before talking about random error, we will talk about the difference between the word systematic, the word random, and between the term systematic error and random error. Then we look at random error, we wrap up if there are any questions, and then we move on. So this slide is to explain the difference between the term systematic and random. When we refer to something as being random, we mean that it occurs in a way that it can't really be predicted. So let's take an example with systolic blood pressure. Systolic blood pressure is a measure of the strength with which the heart is pumping blood in the body. If you take repeated measurements of systolic blood pressure in an adult at rest, you will likely obtain different values that do not follow any clear pattern, or values that can be really predicted. Like a value can be high, another one will be low. These values will be changing about a certain average baseline value. This type of variation, which occur in any direction, is said to be random. So as you can see here, I hope you can see the mouse, the mouse that I'm using to point these points. Can you see the mouse? The cursor? Okay, they say no news means good news.
Yes, we can see.
Okay, great. Thank you very much. So these points represent random variations. So when you take a measurement, you take only one, you can't know whether the next one will be higher or lower. So that's random. Now, suppose that our subject receives a phone call with some exciting news. So this will likely raise their blood pressure in such a way that any subsequent measurements will be consistently higher than those before the phone call. The values will still have some random error in it, but will be consistently higher than the baseline that we had before the phone call. So the fact that we know that phone calls with exciting news makes the heart to pump faster and stronger, we can already predict that whatever measurements we are taking after that phone call is going to be higher than the measurements before phone call on average. So this type of change, this type of variation, whose direction can be predicted easily, is what we call a systematic variation. So the term systematic means that every time you repeat that same situation, it's going to happen in a way that's well understood or can easily be predicted. Random error, we don't know the direction. We can't say that if you go and measure, it's going to be higher than the baseline or lower than the baseline. That's it. So random error mostly comes from sampling variation. So sampling is the process of selecting a number of subjects from all the subjects in a particular group. It is so important because it allows us to answer questions about the population of millions by looking at just a few hundreds. The downside of sampling is that studying different samples from the same population will inevitably give us different results. This phenomenon is called sampling variation. So it just means that if you want to know the prevalence of HIV in Cameroon, if you really want to know it, you have to test everybody with a perfect test. So if in Cameroon we are about 30 million, you need to test every Cameroonian. And then you have a test that has a specificity of 100%, sensitivity of 100%. Then you can be sure that you have no sampling variation. What you have is the truth. But this cannot be possible because it's too expensive and we don't have time. So what we do is that you have to sample. So you sample, take into consideration the desired precision. And when you're sampling, you know that you are giving up precision. So that's it. So sampling variation is just the fact that if someone samples 300 Cameroonians, another person samples 300 Cameroonians, a third person comes and samples 300 Cameroonians, they will have different values for prevalence of HIV. And that difference is normal because we have not seen everyone. We have just randomly sampled from the same population. The values will be similar, but not the same. And that change is sampling variation. So systematic error is also called bias. So systematic error goes with bias, goes with accuracy, and it's basically a predictable difference from the truth. So predictable because we know that you are supposed to take the ages of, I don't know, you want to take the average age of people who live in Dibombari, and you go and you're recruiting, I don't know, you are going to recruit only, let's say, in primary schools, secondary schools, and universities. You realize that you are inducing bias, you're introducing bias in your study because your age at the end of your study is going to reflect young people. So your age will be biased in a way that it's going to be lower than the average age of the population. So now I can already tell someone that this is what's going to happen. I can predict the direction of the deviation from the truth. That's why it's called systematic error. It's an error which can be predicted. There are so many types, but they could be grouped into 3 that we are going to see next week. So this is, in the next couple of slides, I'm just going to explain again what I've already explained, but using diagrams. So if you had no sampling error and no bias, your result at the end of your study would exactly be the truth. So this means that now if you have no bias, but you have sampling error because you didn't study everyone in the population, different samples will give you different results. But since the error is random, some studies will give you values above the truth. Some studies will give you values below the truth. But the average of all these studies, which is usually done in systematic reviews, is going to give you the truth or something that's really like the truth. So this is the scenario when you have no bias and only sampling error in different samples or in different studies of the same population. The average is still going to land at the absolute truth level. Now, this is what happens when you have sampling error with bias. So bias is systematic error. So this is when you have random error and systematic error. So every time you're going to do the study, the value is going to be either systematically lower than the truth or systematically higher than the truth. You still have random error giving you these points about this average. But at the end of the day, the average of all the studies you've considered is going to be shifted in a specific direction, provided that all these studies make the same error. That's why I've subtracted here. So if you make the same systematic error every time you sample people, all your results are going to be shifted in the direction of the error, of the systematic error. So it could yield an underestimated result or an overestimated result. So the example of people of the study where you want to get the ages of people in Dibombari is actually an example of an underestimation, because if 10,000 or if, let me say, 20 researchers carry out the same study the same way, they are all going to have an underestimation of the true average age of people in Dibombari. Now, I like to take, this is a diagram that is very popular. I try to tune it a little bit and add Nicky Larson. We know Nicky Larson, for those who watch cartoons, back in the days when manga was still manga, the French TV channel for Japanese anime. Nicky Larson, or City Hunter, or Riho Seba, is a very precise shooter. He's precise and accurate. So these two terms are terms that sometimes are used to replace random error, systematic error. So precision is an issue of random error. And then accuracy is an issue of systematic error. So when Nicky Larson shoots a point, the center of this thing, he is likely going to, if he shoots 20 or 100 bullets, he is likely going to hit the same spot or just around the same spot every time he shoots. And the size of this circle is kind of a measure. This pink circle you're seeing here, it's kind of a measure of your precision. That is, every time you shoot, how likely are you to shoot around the same point? So when we take the average distance from the center of your shots, what is the size of that distance? So for Nikilas one, is going to be very small. So when you are less precise and you are accurate, you are looking at the real target. You are accurate. You are not biased. You are really looking at the right target, but you are not having enough practice. So whenever you shoot, the points go a little bit far from that point, from that real target. So that's what you're going to have if you are a shooter with accuracy without precision. So it's just like taking a study. It's like carrying out a study with a small sample size, but having a very thorough methodology. So if you have a study, randomized control trial, you're having 7, 8 people. No, 7, 8 is exaggerated. But let me say if you have like 20, 30, because people carry out randomized control trials with thousands of subjects to have this type of precision. So here, maybe if you have like, depending on what you're studying, actually, if you're carrying out your randomized control trial, you have 30 people, 40 people, you might have an accurate design, but a less precise study, a less precise result, meaning that you can be at this pink point here. But you see, this pink point was a result of an accurate study, but the lack of precision has made the point to be quite away from the truth. So I'm not saying that random error is better than systematic error. Systematic error is worse. Both of them should be taken into consideration because we don't usually conduct studies many times. The only time we do this type of things and then get the average is in meta-analysis. That's why meta-analysis they will remain the best type of studies, because actually they help us to consider the average of many studies when the studies are homogeneous or when there's very little heterogeneity. So let's go. So what do we do when you have this type of situation? So you carry out a study, you have the impression that the study is revealing something interesting, but the sample size was little, and the way the study was conducted exposes the study to very little very little bias. So you're very happy with the results. What should you do next? The best thing to do is to carry on with the recruitment. So if you recruited and it's not been long since you published, or if a study is published and it's not been long since they recruited, maybe they can just try and recruit again so that we can have a more precise estimate. Another solution is that you look out in the literature if you have other studies similar to the one that is in front of you, in case you're a reviewer, or if you are a critical or someone are critically appraising literature, you can look at what other studies on the same population on more or less the same topic have found and try to merge those studies in the way they'll do in a systematic reviews with meta-analysis. Now, when you can have an accurate design. That is, the way you select your sample is good. The way you, measure things from them is proper. The way you analyze the data is perfect. But you study just 20, 15 people. And yeah, your required sample size was like 200, but you had 15 people. It's kind of hard now. So I think there is a threshold. There's no fixed threshold, but I mean, you shouldn't study. I think it's not going to be useful to recruit 8 people and then try to conclude, because you can be this point here. So this guy here is in space. He's actually not useful at all. So I mean, it's small sample is not a bad thing, not at all, but at least there is small and small. So we should try to be at least have a sample size that will confer us a type of imprecision that can be tolerated. So this is the case of a precise and inaccurate study. So this is a very large study that was really poorly designed. So you have the appropriate sample size. The sample size you have is just amazing. But maybe, I don't know, you selected your participants with an invitation letter that will automatically make some people in the population angry or not happy or not eager to respond. For example, in Cameroon, we're a bilingual country. If you want to carry out a study in a place like Yaoundé, which has a lot of people speaking French as their first language and lots of people speaking English as their first language, you realize that if you pass on an invitation letter that was not correctly translated or that doesn't even have a translation, you are going to bias the population that will come to your study. And we know that culturally, we have some differences. So it's important that you try to integrate all the different social constructs or social strata in a population when you are inviting people to avoid errors at the selection stage. I'm just talking about selection bias here. We're going to look at the different types of biases next week. Any question? Okay. All right. Any question? Okay, because I'm seeing some people are activating their mics. So let's go. Yes, so the selection bias that you will have, even if you have a very good sample size, your study was heavily funded, you're studying 20,000 people with a consortium of people from Canada, Cameroon, Ghana, Nigeria, and you have a poor conduct, this is where you learn, which is quite unfortunate. Now, thank God, statistical analysis can come in here to help you. They always say that a good design is far better than any fancy statistics. But, sometimes we can't avoid it because it might be the only thing we can do to save our research. So we have methods to correct bias during statistical analysis. So I know a few of them, like Monte Carlo sampling, resampling method, something like that. Or you do what they call bias analysis. Sometimes it's not even very complicated. You just take the worst case, best case scenario. I hope we'll be able to do, to have a presentation on how to correct bias during statistical analysis in a later session. Okay. So these are the 4 scenarios. So this is just a summary of what we have seen. So your study can be precise and accurate, meaning that your sample size is big and you are making very little methodological errors, or methodological errors. And then your study could be precise and inaccurate, meaning that you have a very good sample size. That's what happens most of the time. You have a really good sample size, but the way you're collecting your design is wrong. And then here you can be imprecise and accurate. So accurate just means that there is very little systematic error. There is very little bias in the way the participants were selected, the way the things were measured, the way, etc., etc. It could be imprecise and inaccurate. This is really, really, really sad because we can't do anything. There are too many things we have to do to this study to be able to make it come back to the center or be confident that whatever estimate we have, because remember, in primary studies, we only have one of these points. And if you read the method and you have the impression that the method was inaccurate with little precision, then you just say that maybe that research was a waste. This is where I want to believe that many studies I have coached rely. So the studies I was coaching, I wasn't coaching like a coordinator. I was more of someone that will come, when you leave medical school in level 7, when you finish level 7 and you like statistics, you can use, SPSS. You can always have students that come to you so that you can help them analyze. So I don't analyze data for students. I actually help them to analyze themselves. But back in those days, I was doing that with a couple of classmates. And when I look back, when I retrospectively assess what I would used to do, it was around here. Okay. So that's why I created this series. So today we are going to talk a little bit about random error. We have a lot of time. We are going to end way before 10. Maybe we are going to end at 9. But yeah, if you have any questions, you can take us up to 10. So random error We're going to talk about random error in the context of health research. So if every subject in a population of interest was included in a study, as it is done in a census, there would likely be no random error, given that provided all the measurements are precise. So random error in a result of a study mainly comes from the fact that only a relatively small group of people are selected from the population of interest. And that's usually called sampling error. So the other type of random error, which is also common, is measurement error, but we're not going to talk about that. Okay, we have a sample. We have a population of interest. We don't know the parameter. So we want to determine the prevalence of diabetes in a certain country. I just called it Stevania. And we randomly sample 130 people and 16 test positive. It will give you a prevalence of 12.3%. If we only do this, we're going to call this our point estimate. Now imagine that we have the luxury to resample these 130 people from this Stevania. We might do it and find out that we have 13.8. We do it again. We might have 10.0. We can do it again and have 7.7. Do it again and have 15.4%. If we could have the luxury to do all this and then take the average, we're going to have what they call a best estimate, which is exactly what is being done in a meta-analysis. So there are so many different methods, very complex methods nowadays to do more complex things, but this is a very simple example of what meta-analysis does. So generally, we don't have that luxury. That's what's unfortunate. So if we build the histogram of the sample estimates, most sample estimates will be concentrated within a certain range of values in the center. This range of values is known as is supposed to be what we have as confidence interval, and it is mainly determined by what we call standard error. So roughly, the standard error is the measure of the average distance between the best estimate, represented here with the gray diamond, and other samples. So there are just big terms here, but what I'm saying is that it's possible to estimate the average distance between whatever research you've done and the best estimate using an analogy to what they call standard deviation. So these are technical terms. I didn't really make this PowerPoint to talk about the technical terms, but basically we can estimate what other studies could have had if we had access to this type of information. Excuse me, I'm just accepting. Some people are coming in now. Okay. Oh, I'm having some words of encouragement. Thank you very much. Thank you very much, Dr. Atangina. So let's dive into confidence interval. And if you would like to understand or have some more explanations on the intricacies behind. Hello, does anyone want to say something? Okay, let's continue. So if you want to know what happens behind this confidence intervals and all that, we can have another session on it, but I just want to explain the essence of it so that we can apply it. So the 95% confidence interval is certainly the most popular confidence interval. It is the interval which will contain the true population parameter for 95 out of 100 random samples of a particular size drawn from that population. In other words, if we conduct the same study on 100 random samples of the same size drawn from the same population, 95 out of 100 of them yield confidence interval that would contain the true population parameter. So this is something formal that I kind of got from Essential Medical Statistics, which is the book that I showed at the beginning, which is probably the most popular book in medical statistics for people, for health researchers that want to know how to handle their data themselves, which is highly recommended, because they recommend health researchers to be really more involved in the statistics to avoid making typical errors. Because if I am a specialist in, say, I don't know, cardiology or endocrinology, and I have research questions and I have published before, I'm more likely to get funding to do really big research, because everyone would say I'm a great cardiologist and I have already published and everything. Now, to avoid making mistakes with all that money that they will put in at your disposal, it is good that you get involved with statistics. Statistics is not mathematics. It's problem solving in a clever way. Here I'm quoting Julian Higgins, who is probably one of the greatest, or I don't know, one of the most popular statistician in meta-analysis, and whom I had the chance to be the student. It's not about mathematics. It's just a clever way of doing things to avoid errors. So it's really problem solving. So when you have all that finance, all that budget to do, it's good that you use the budget and you also use people's time, because a lot of participants who get involved, you use it in a way that is effective. So it's important to go back to these basic principles. And if you have more time, you try to get as much as possible involved in the analysis. So Essential Medical Statistics is a book that you can easily have online. You can download it from Amazon, or it's not really expensive. It's very accessible. So coming back to confidence interval. Hey, what am I doing? Oh, sorry, excuse me. So coming back to confidence interval, there is a very simple way to calculate the confidence interval for each single study, in a way that we don't need to get this best estimate anymore. So there is a very simple way for you with your single study to estimate an interval within which you are likely to have the true value. Oh, okay. So study 1, the one we conducted, is giving us this confidence interval. This line represents more or less the true value. So if you do a meta-analysis, this line will be the result of your, how can I put it, would be your combined result, this line. So you have the cube here, and this line will be your combined result. And each of these study will be an estimate with a confidence interval. So you see that this line will cut across all these estimates in most of the cases. So if you had 100 studies like that, if we count, you realize that this line is going to cut across 95 out of the 100 studies. That is what confidence interval is. So it's an interval within which you are most likely to have the true population value. So to be more precise and accurate in the definition, I would say it is the interval which will contain the true population parameter for 95 out of 100 samples of a particular size drawn from the population. Okay. So an important remark to make here is that for your confidence interval to be valid, your sample should be of an acceptable size. Because if you sample just 2 people, the confidence interval will be so big and not useful and so inaccurate. And even the thing that works, that permits us to have confidence interval, is not going to be applied to your particular scenario with a very, very little sample size. You need to have a sample size that's acceptable, like 20, 30, things like that. 10, in certain cases, 10 can go. The other condition is that your sample should be a random sample. That is, each participant in each eligible subject or each eligible individual in your population of interest should have equal chances of being selected. The word random is so important because what comes into effect and permits us to make all these predictions is what they call the central limit theorem. So the central limit theorem is a very popular theory, which is really central because it tells us that no matter the underlying distribution of whatever trait you're trying to measure, if you're sampling randomly, the sample results are going to give you what looks like a normal distribution most of the cases. So you can always go and check more on that later on. So the true population, so there's a possibility that the what you have, your confidence interval has little to do or nothing to do with the true value, but that is unlikely because it happens just 5 out of 100 times. But who knows, maybe your study could be one of those 5% which doesn't contain the true population value. Please bear with me a second, Elisa. Let me answer this call and redirect the person. So what's the margin of error? So the principal thing that characterizes a confidence interval is a margin of error. So your confidence interval is between this and this. And if you divide the space between the lower and the upper interval by 2, you have your margin of error. So the clever thing here is that the margin of error is kind of a measure of your precision. If your margin of error is high, your confidence interval is high, it means that your study is not very precise. If your margin of error is low, confidence interval is low, means that your study is very precise. So, sorry, if you have to get back here, it means that the estimates of all these studies will be really, really narrow. And all these studies will have like a skeleton. So actually, they call this type of thing a forest plot. So if your confidence interval is narrow, it's going to be so beautiful. You have some points that are going to just be oscillating around this line. It's going to be so nice. But when your confidence interval is large, you have a point here, you have another point here, you have another point that is close, another one is here. This one is very, very far. And if we continue, they will continue being so far because the sample size might not be suitable for the study. So margin of error is what characterizes your level of precision. So random error goes with precision, precise. Now this is a formula to calculate standard error for a prevalence. These formulas that are available online with statistical packages, you can always compute them without using your calculator. But the point I'm just trying to make here is that the margin of error that we usually consider is plus or minus 2 z-scores, 2 standard errors. Plus, so you have the mean minus 1.96 to be more precise, standard error, and the mean plus 1.96 standard error to give you the upper bound and the lower bound of your confidence interval. Confidence interval can be calculated for anything. If you are studying a numerical quantity, confidence interval can be calculated. What again did I want to say? So the fact that we consider 95% is really just arbitrary. From the property of a normal distribution, we know 95% of data is found within mean minus 2 times standard deviation approximately, and mean plus approximately 2 times standard deviation. At the time of Pearson, the great statistician, but that's not too far. That's like in the 18th or 19th century, something, or 20th century. They just declared that if you miss the truth 5% of the time, if you miss the true value 5% of the time, it's not, how can I say, it means that you were really, really precise. So if you miss the truth less than or equal to 5% of the time, it means you're really precise. There is no study behind this 5% and 95%. There is no rationale behind it. It's just something we do conventionally. It helps though. So yeah, if you have your standard error, you have your margin of error. So generally, standard error times 1.96 gives you the margin of error. And if you take your point estimate, which is what you have after your study, plus the margin of error, and you take your point estimate, what you have after the study, minus margin of error, you're going to have the lower bound and the upper bound of your 95% confidence interval. So that's just what I wanted to show here. So for this particular scenario, where you have 130 participants and you're trying to get the prevalence of diabetes in a certain population, is going to give you 12.3% point estimate what you got from your study, and upper bound of your confidence interval 18%, lower bound of your confidence interval 6.6%. Now, if you were the Minister of Public Health of Cameroon and they tell you that this is the prevalence of a certain disease, or you're the Minister of Public Health of Tivania, the country, and they tell you that this is the confidence interval, you realize that it's too broad. It's too broad to take any action. It's too large. And that's the issue with precision. We know that you cannot have 100% precision, but at least it's possible to design your study to have a precision that gives you something that's useful. You said that the objective of your study is to produce a prevalence that will be useful, but that will be helpful for decision makers, but you produce this. If your study is unbiased, it can still be useful. If your study is unbiased, but well, we need to continue recruiting, or we need to carry out the study again and mix and combine the estimates. So that's the thing with precision. There is nothing wrong with small studies, but the problem is that they give confidence intervals that might not be applicable. But they're not useless, provided there are no bias. Because to me, the main problems of studies that I've seen in Yaoundé by especially thesis students, because I believe that they are the ones that produce a lot. Every year we have about 1,000 theses that are being produced or more. Talk less of people doing masters and other types of years. You have thousands, and there is a lot from my experience. I've seen over 200. There is a lot of systematic error in it. Too much that most of the things can be applied. And we can look into that. But as I said, we'll talk about systematic error in the session next week. So here I want to talk about the different factors that affect the precision. So the first thing is what we've been talking about, is the sample size. So the larger your sample size, the better your precision. So I've written it here. Larger sample size, smaller sampling error, higher precision. Smaller sample size, larger sampling error, lower precision. And I would like you to notice something, is that at some point, to gain an extra precision, you need to add a marginally higher number of participants. So in the beginning, so 130 studies is giving you this, 6.6 to 18. 1,300 is giving you 10.5 to 14.1. So that's nice, but you see that 14.1, someone can argue that's not too different from 18%, but you've multiplied your sample size by 10. That's why I say small study is not necessarily bad, because if you don't have money, you might not get into this type of studies, especially if you're testing things. If you're testing things, you're doing this type of study, the marginal gain per cost, I'm talking about the financial cost, the time that people would take to take part in your study, the ethical things or the harm you might cause people in doing your study. When you take that into consideration, the fact that you're living from 130 people to 1,300, it's necessary to ask yourself whether it's necessary, whether it's important to take this number of people and gain this type of precision. Is it really worth it? So this is a case-by-case thing that you have to analyze if you're conducting a study, but these are things you need to take into consideration. And the objective of the study, is it to implement something? Is it to scale up something that was tested at a smaller scale, etc.? Another thing that affects the sample size is the relative size of the target population. So we usually have the target population, the population of interest, people suffering from arthrosis, young children, young adults suffering from back pain. That's my target population. Or women with dysmenorrhea. That's my target population. There are millions of them. And depending on the subject, the target population can be really high. When your target population is big, like above 100,000, in statistics, is considered as being infini, like unlimited, like infinity. But when your sample size is like a few thousand, a few hundred, now we have to do what they call population adjustment for sample size. If you needed to study 600 participants to make a conclusion on 100,000 people, you will have to use less participants to make a conclusion on 1,000 people. Let me take an example of where this applies. You know, in Cameroon, we don't have too many patients on maintenance dialysis. Now we have much more than maybe 10 years ago. 10 years ago, I think there was only, or 20 years ago, there was just one center, I think in Yaoundé, then the one in Douala, with a couple of tens of patients on maintenance hemodialysis. But now I think we have a center or two in the big cities, and then at least one center in the other cities. And the total population of patients on maintenance hemodialysis is about 1,500, something like that. And that population is not big enough to consider the population as an infinite population because there are few of them. So if you want to study these patients, you can take a random sample of less than what you would have taken under normal circumstances. So this is something that affects the size of your target population. It's something to bear in mind. The calculation to correct is not really important right now for this presentation, but it can be important for your study. So I'm just going to waive that. But you can always come back to it. It's not hard. And there are many papers talking about population correction for sample sizes. Okay, this was a slide on it. I think I put a reference. I hope the reference is still around, where you can get the paper that discusses the population adjustment. Yes, this is still on the finite population correction. Sorry. Yeah. So here I was taking an example. I was saying, okay, we talked about Stevania. Okay, we say Stevania has 2,230,000 people. And if you are sampling this population and you're considering the actual size, you're not considering that the population is infinite or unlimited or infinite, your finite population correction is going to be 0.999999. And it's close to 1. When it's 1, it means that you could just consider that it was infinite and just go ahead. Now, if your sample size or your population, the target population is 500 people, maybe people who migrated from a war zone and they settled in another city, they are like 500, they are like 1,000. If you want to make a conclusion on this 1,000, you will not require a conclusion of the same precision on these 1,000 people. You won't require the same sample size as if though there were so many in the target population. So you have to apply the finite population correction. In this case, it's giving us 0.86. Well, someone will argue that 0.6 is 0.999 is almost the same thing, but yeah. The same study in these different populations with the same sample size of 130 is going to give us the same point estimate if we're lucky. But look at the confidence interval. Here, 130 people is going to yield a confidence interval of 6.6% and 18.0%. Here is going to give us a confidence interval of 7.4% and 17.2%. So we have gained some precision here. Now, depending on the cases, the precision we have gained could be considerable or negligible. In this case, it's a bit negligible, maybe because of the variance of whatever trait we are measuring. So the key point I'm trying to make here is that considering the size of the target population helps you to do a better estimation of the required sample size and have better precision and to minimize random error while economizing resources, time, money, the participants, etc. So a question that's very common is that, is bigger sample size always better? I think that we have been answering this question all through, like progressively. We've been providing answers to these questions, to this question. So the things I think we need to take into consideration is the cost, is the time, and is the benefit and harm. I've been talking about prevalence because prevalence studies are some of the simplest studies, I guess, that they are just in French they say how do they say that? How do they call that thing that we do to predict who will be president in France? It always comes before the results of elections. Can someone help? In French, where they give participants sondage. Oh, thank you very much. Sondage. So sondage is quite a simple thing to do. You can do it through telephone. You can do it interview in the streets if you have a lot of people like human resources. That's why we've been talking about this. But I mean, what I'm saying is applicable for whatever type of studies. So long as the study is quantitative, you're trying to measure something. Could be an odds ratio, a hazard ratio, a risk difference, difference in means, anything. It applies. So you have to weigh between all of these: benefits, harm, the time you take, the amount of money that you put in, because most studies are funded by the government or by a certain government or by, yes. So precision is affected by variance. So what's variance? Variance is just a measure of how individual participants' values differ from the mean value of the group of people. So generally, we'll talk about the population variance. That's the variance of the population of interest. If the population is too heterogeneous, here I'm just using the word in English, which means that people too different. So if the population has a very large variance, you will need a very large sample size to capture accurately the type of information of interest. Oh, someone wrote sondage. Thank you. You need a very large sample size to capture the information with a certain precision. But if the population has a very little variance, that is, if you're interested in getting the mean age of people suffering from, I don't know, any disease, heart failure, if you want to get the mean age of people suffering from heart failure, and then in the population of interest, you have children who suffer from heart failure, young children, and then you have adults, you have old people, the variance is going to be really high. And to be able to capture this information with a good enough precision, you will need a very large sample size. This is taken into consideration in the sample size calculation, in all sample size calculations. And it's just good to know that and to expect so it helps you to know that, wait, given how heterogeneous this population is, how managed this study took only 100 people? Like, I doubt it's going to be nice. And when you start thinking like that, you realize that for certain things, the researcher won't give confidence interval when the researcher was supposed to. And you realize that maybe they didn't give confidence interval because it was too big. So they couldn't put it in the paper, or else they would say that their research was not useful or not helpful. And generally, they encourage people to report research in the most transparent ways so that appraisal can be complete and unbiased and precise, unbiased. So whether your sample size is too small or your variance is too big and your confidence interval is too big, it's always nice to report everything so that people who read it can understand what's going on and they can better adjust if they want to carry out studies, or they can better take decisions if they have to base themselves on your studies to maybe treat a patient or, I don't know, promote a certain program for health promotion, for example. So this is a very simple example showing sample A and sample B. Actually, the variance in question here is the variance of the population, but I just took samples so that we can see what's happening. So in A, we have a variance of 10. In B, we have a variance of 2.5. And then here, the confidence interval where the variance Yes, the confidence interval where the variance is large is going to be very big, because 18 can be somewhere here, can be somewhere here, 26 will be somewhere here, so it's very, very large. And the confidence interval where the variance is low is going to be smaller. 20 will be somewhere here, and then 24 will be somewhere here. So that's it. There is this 0.5 we like to put when we are calculating sample size for sondage for prevalent studies. When you don't know the prevalence of a situation, of a certain health condition, and you want to get the biggest possible sample size to have the precision that's required, we usually throw a 0.5 there. So this 0.5 is not the 0.05, it's 0.5 of prevalence, that's 50%. And it's not arbitrary, technically speaking. It is the prevalence, the hypothetical prevalence that's going to give us the largest possible sample size so that we don't miss it. So this is just something I added here just for culture generale. This is more on sample size calculation. It's not necessary. Okay, another thing that affects the amount of random error is measurement error. This is very, very important because we don't use gold standard. We generally don't use gold standard, what they say, the gold standard to measure parameters in a population. Because if you have 1,300 or you have 20,000 people and you want to diagnose, I don't know, brain cancer, it will be really hard to do an MRI to all these people. And we can even start to doubt whether it's going to be ethical. I don't know. So we have to use another measure, like another practical, simple, and cheap test that everyone can do. Because if you want to do an MRI on 20,000 people, you have to pay a radiologist, and it's going to make the research so costly that maybe it's going to be a considerable proportion of the budget, especially in Cameroon when the budget is a couple of billions of dollars. So measurement error is another factor affecting the precision of results of a study. This is because the observed variance is actually the sum of the true variance of the property of interest and the variance due to measurement error. Measurement error comes from a good number of sources, including biological fluctuations, the fact that no device is perfect, and for studies, we don't use devices that are perfect generally. So you can have really, really big studies that use gold standards because they have the funds and they have calculated the impact of not doing the study, and the impact is too big that they can't avoid themselves from doing the study that way, prevent themselves from doing. So that's when they can actually use gold standards, but we don't use that. And then the measurement procedure. So the measurement procedure can cause you to have measurement error. So the external environment can also add to measurement error. So if measuring devices, or if the measuring device used in the study is really imprecise, or all the measuring procedure is not precise, it will reduce the overall precision of the final results. This is something we don't like. My dissertation at the end of my master's was on measurement error and how it can lead to bias. And while I was studying that, I was also studying how measurement error generally just causes imprecision everywhere. And the key point of the dissertation is that everyone knows that measurement error exists. Everyone knows that taking 2 blood pressure measurements and doing the average can help, or taking 3 of someone at rest can help to reduce measurement error. But very, very, very few people do it. And you know, we've realized that you can gain over like a 30% precision by just taking into consideration measurement error in very simple ways. Like I've said, taking multiple measurements and taking the average, or using very simple methods like regression calibration to mitigate measurement error and avoid what they call regression dilution. We might talk about it in another session. So this is a very big issue. Like someone is just climbing the stairs. If you're doing a study on blood pressure, and then participants, maybe they take blood pressure in your hospital after going up like stairs, and then the participant just comes, and then the recruiter, I don't know, the person taking the parameters just says, "Good morning, madam. Please, yes, oh, it's for the study. Okay, please, can you just present your arm? Let me. Yeah, you were polite, but that's not correct for the procedure, because measurement of blood pressure requires that you stay calm for some time, maybe 5 minutes, and then we come and then we take your blood pressure, and then we wait again, we take your blood pressure. So those are things that we neglect. But even if we calculated the right sample size, the precision can still be catastrophic if the measurement procedure is not good. And like I said, measurement error is not only an issue of precision, it's equally a huge thing when it comes to avoiding bias because of what we call regression dilution. Another thing, just to end, just where I've soon getting to the end of this presentation. So another very important thing that we need to take into consideration, we might not even take it into consideration because most of those things are good things, is the way we control for confounders in studies that have as objective to establish a causal relationship. So in studies, to determine the causal relationship, we often want to remove the confounder from the analysis we are doing. And we use regression, multiple regression. There is a second book that I referred up there that was part of my references, or like the books from which or where I got most of the things I'm talking about right now. It's What If by Professor Miguel Hernan at Harvard and James Robbins. In that book, they describe the modern way of handling confounding, which is totally different from what we are doing or have been doing with students. So, when you are adjusting for confounders, according to a certain paper I read, which I'm probably going to give you in the group, you are most likely to improve your precision. If you're adjusting for pure predictors, so what do they mean by pure predictors of outcomes? They are variables that affect your outcome or that your outcome affects. When you kind of condition on them in a multiple regression model, you kind of increase the precision. So this last to improve your precision. Now, something that is bad or that can worsen your precision is if you condition on a pure predictor of exposure. So this concept of pure predictor might not be universally agreed, so I'm not going to waste a lot of time on that. But it came from a paper that looked quite interesting. We will talk about conditioning on confounders and other things that can bias our estimates next week, and briefly talk about the rules of deseparation, which is the underlying concept that allows us to understand what to put in a regression model and what not to put in a regression model when you're trying to have an unbiased or when you're trying to reduce bias, especially in observational studies. Okay, next slide. Okay, this is a summary of what we have discussed so far. We have practically come to the end of the presentation. So error in research, in summary, is the difference between what you have at the end of a study and the truth, which technically no one knows. Error has a random component, mainly attributable to sampling error, and a systematic component called bias. Sampling error is mainly due to sampling variation, while bias could be caused by any mistake in the planning or execution of the study. The amount of sampling error in the result of a study is given by the standard error, which is mainly determined by the sample size and the variability of the property of interest in the population. And in the sample to a certain extent, although the amount of bias may not always be directly estimated, one can often predict whether the bias led to an overestimation or underestimation. Random error defines the precision of the result, while systematic error or bias defines the accuracy of the findings. Overall, we can say that the precision and the accuracy of a study allow us to assess the extent to which the findings could be applicable to a specific setting. So we are going to end our presentation with this little quote by Professor Doug Altman, who is someone I really, really, really admire. Fortunately, he died a couple of months ago of, I think it was, I don't know, cancer or something. So he said, we need less research, better research, and research done for the right reasons. And I strongly agree with my little experience with research in the Cameroon context with students. So thank you very much. Are there any questions?
Thank you very much. It was very interesting.
Thank you very much, Doctor. Do you have any questions somewhere? Is there anything I can come back to? There is space here.
Oui, bonjour docteur. Merci pour la présentation.
Merci, Doc.
Ok. Peut-être parce que la présentation était en anglais. Est-ce que vous pouvez un peu venir sur le rappel de la différence entre une erreur aléatoire et une erreur systématique, et puis des exemples dans chaque cas?
Ok. Je vais prendre un exemple.
D'accord, merci.
Ok. Donc, prenons, disons que vous êtes en train supposons que vous êtes en train de mener une étude pour déterminer la prévalence du diabète. La prévalence du diabète dans un pays, peut-être disons le Cameroun. Et que dans votre study design, vous avez pris juste les gens qui sont à l'hôpital, par exemple. Vous allez étudier les gens à l'hôpital. Quand on étudie les gens à l'hôpital, on a tendance à avoir beaucoup plus de malades qu'on aurait eu si on avait étudié les gens dans la communauté. Et donc, cette façon de procéder-là expose votre étude à un biais. Le biais, c'est le même nom, donc c'est un synonyme à erreur systématique. Pourquoi ça s'appelle systématique? C'est parce que je peux prédire la direction de l'erreur. Donc, comme vous êtes allé recruter à l'hôpital, je peux prédire que votre estimation de la prévalence sera supérieure à la vérité, à coup sûr. Parce que les gens à l'hôpital ont tendance à être plus malades, ou c'est plus facile de trouver un diabétique à l'hôpital. Vous voyez un peu ce que je veux dire, non? Ça, c'est pour systématique. Donc, erreur systématique veut dire que de par la manière dont une estimation a été établie, vous pouvez déterminer la direction de l'erreur ou de la direction de la déviation de la vérité. Vous voyez un peu. Maintenant, erreur aléatoire, c'est un peu, on ne sait pas dans quelle direction. On sait que c'est présent. On peut un peu déterminer la taille. On peut prédire la taille. Mais la direction, c'est un problème. Par exemple, je donne un exemple. Ici, là, dans cette présentation, on a beaucoup plus parlé de l'erreur aléatoire due au défaut d'échantillonnage ou de la taille d'échantillon. Donc, s'il y a 1000 personnes dans où il y a 100 000 personnes dans un village et que vous voulez avoir l'âge moyen des gens dans ce village et que vous prenez, disons, 20 personnes. Quand vous allez prendre l'âge des 20 personnes là qui sont les participants de votre étude, quand vous allez mesurer leur âge, vous allez diviser par 20 pour avoir la moyenne d'âge. La moyenne d'âge là va être accompagnée d'une estimation, d'un intervalle de confiance. Votre intervalle de confiance, comme vous n'avez considéré que 10 personnes, sera très élevé. Pourquoi? Parce que quand vous prenez 10 personnes d'une population, les 10 personnes-là peuvent varier de manière qui ne va pas, d'une manière qui ne va pas pouvoir vraiment vous permettre d'avoir une certitude de la valeur. Vous voyez un peu, non? Et vous ne pouvez pas savoir si la moyenne des 10 personnes-là, c'est une sous-estimation ou c'est une surestimation. Vous ne pouvez pas le savoir d'emblée. Donc, je ne peux pas avoir une étude avec une taille d'échantillon qui est très petite et directement dire que c'est une sous-estimation ou c'est une overestimation. Vous voyez un peu, dans le fait de ne pas pouvoir prédire la direction. Je sais que comme il y a 10 personnes, c'est pas précis. Mais je ne peux pas dire, le fait de savoir qu'il y a 10 personnes ne me permet pas de savoir s'il y a une surestimation ou une sous-estimation. Donc, c'est un peu ça, l'erreur aléatoire. Un autre exemple d'erreur aléatoire, mais là, je vais plutôt parler en termes d'erreur de mesure, c'est que si je prends votre poids tout au long de la journée, votre poids va varier à cause de beaucoup de choses qu'on ne peut pas facilement prédire. C'est-à-dire que votre poids peut varier parce que vous avez mangé ou parce que vous avez transpiré, vous êtes allé aux toilettes, vous avez bu l'eau. Et si vous ne mesurez pas ça, quand vous prenez votre poids chaque heure, le poids va dandiner. Et vous ne pouvez pas savoir à coup sûr que comme je monte sur la balance là à 10 heures, mon poids sera une surestimation ou une sous-estimation. Le fait de ne pas savoir quelle est la direction de l'erreur, quelle est la direction de la déviation de la vérité, c'est ça le fait d'être aléatoire dans l'erreur. Vous comprenez un peu ce que je veux dire?
Je comprends mieux, docteur, merci.
Oui, c'est un peu ça. Est-ce qu'il y a une autre question? Do you have any other questions?
Oui, docteur, vous avez parlé de precision and accuracy. J'ai pensé que accuracy, c'est précision en français, je sais pas.
Je pense qu'au niveau des langues, il peut y avoir des divergences. Il y a des gens qui pourraient appeler certaines choses autre chose parce qu'il y a d'autres termes comme reliability, etc. Mais je ne voulais pas rentrer dans tous les méandres